going? Recording this last short and sweet little lecture for valence bond theory. All right. So this is also going to go in really nicely with your Math 8 assignment that I've got right in front of me here. And part 1 is all about valence bond theory and the hybrid orbitals. Okay. So what I want to do is walk you through how we're going to transform these wave functions into our XYZ coordinate system, because as it turns out, it's really a matter of convenience for being able to look at this in XYZ, particularly for this valence bond theory and hybridization. Okay. So I'll remind you, let me just scroll back for a second here. The sp3 hybrid orbital is a superposition of 2s, 2px, 2py, and 2pz atomic orbitals. So we will first need to start by putting together those orbitals. And like I said, because of this xyz designation in our p orbitals, it's convenient to turn this back into Cartesian coordinates. So I'll remind you, so the first wave function we want to look at is the 2s wave function. And I'll remind you that psi2, 0, 0, n equals 2, l equals 0, ml equals 0. And we break that up into the radial wave function, and we break that up into the spherical harmonic wave function, right? The r2, 0, and the y0, 0. Okay? So the R20 is given by this equation here, right? 1 over root of 8 times z over a to the 3/2 power, where we know a is the Bohr radius, and 2 minus rho times the quantity e to the minus rho divided by 2, where we also remember that rho is 2zr divided by Na. Okay? Well, because we know that n is equal to 2, then this rho, 2zr divided by 2a, just becomes zr over a naught, all right? And also, because we're using the Cartesian coordinate system, we're going to take advantage of the Pythagoras, okay? Square root of x squared plus y squared plus z squared. So anytime we see an r, we're going to replace it with this big nasty thing, square root of x squared plus y squared plus z squared. So now, putting these equations together, there's also something that I've done here for you to make your lives easier. And what I've done, so I combined these two equations, right? 1 over the square root of 4 pi times this whole thing. And I combined the 1 over square root of 8 and the 1 over square root of 4 pi and simplified it into this chunk right there. Okay, so I just did that algebra for you, and you'll see why in a moment, why I did that algebra to convert the 1 over square root of 8 times 1 over square root of 4 pi as 1 over 4 root 2 pi. Okay. We also notice here that there's my z over a to the 3/2, right? There it is. And there's my 2 minus rho, which becomes 2 minus z over r, zr over a, right? And then e to the negative zr over 2a. Beautiful. So now, converting this over to x, y, z, for this particular, for the 2s wave function, the only thing I have to do is replace anywhere that I have an r with a root x squared plus y squared plus z squared. Okay? And also, I'll remind you that z is our charge here. And on this Mathematica assignment, you're going to use a z of plus 4, which, again, is a matter of convenience. We know that really all of these wave functions are only 1 electron wave functions, right? These are hydrogen wave functions. But I put a z plus 4 just, like I said, for convenience, okay? So the math works out, the visualization of this works out nicely with z equals 4. Okay, so this becomes our 2s wave function and Cartesian coordinate, right? Just the 2s wave function. And so I'll remind you, when we put together all of these bases sets, right, we've just only put together 2s. But we're going to be able to use that equation throughout all the rest of these hybrid orbitals. So for the sp3, right, we just use the 2s wave function. For sp2, right, we can still see our 2s wave function. There it is, beautiful. And for sp, we still have our 2s wave function, okay? So let's come up with the 2p, x, y, and z wave functions, okay? So first, we're going to focus on the 2pz. So there we go. And hopefully remember the 2pz wave function is psi210. N is equal to 2, L is equal to 1, ML is equal to 0. Okay? And so we can break that up into the R21 and the Y10. So here we get this from the R21, this equation. I should have really, we'll say this equation right here. And we know the Y10 is the square root of 3 over 4 pi times cosine of theta. So I'm going to have to plug that into y as well. And check it out, you guys. This is really cool. All of these constants, the 1 over square root of 24 times the square root of 3 divided by 4 pi, can be simplified to 1 over 4 root 2 pi. Yes, it works out. And that's the same thing we got to work out over here, which is cool. So it's very convenient that we can use that same factor. And so now look, we've got a z over a to the 3/2. So there's my z over a to the 3/2. I've got a rho, and I'll remind you, right, because n is equal to 2, rho just becomes z times r over the Bohr radius. So then that rho is right here. Now there's a cosine of theta from the y, and then I put in the exponential, e to the negative zr over 2a. Okay, lovely. So now what happens? Well, we know that r is still equal to the square root of x squared plus y squared plus z squared. Okay, but also r times cosine of theta equals z. All right, and so I'll point that out, that I've got an r times a cosine of theta right there, and that all becomes z. Lovely. My exponential becomes, to the negative z, which remember, the capital Z is nuclear charge, and we're just going to use +4 as a, excuse me, we're going to use z equals +4 just as a matter of convenience, okay? It's not totally physically accurate, but it's reasonably accurate. And then now, look, I've got a z over a to the 3/2, and then the z over a combines with this to make z over a to the 5/2, okay? But now what we can do with this thing is we can call all of this psi210 as a function of x, y, and z. We can just say that this is all equal to z, right, times some function in r, which, recall, that's what we did last time. Okay, we did this in chapter 9, where now my function of r is this chunk and this chunk right here. So all of that is my f of r. And of course, I've replaced r with the square root of x squared plus y squared plus z squared. And as it turns out, no crazy superpositions or anything like this is required, because I didn't full on go through this proof, but we could show, right, those superpositions we went through last time, which was, for example, right, for the 2px, if you recall, that was 1 over root 2 times the p plus wave function. I think it was plus the p minus wave function, right? Well, as it turns out, you can do the algebra and show that all of this just equals x times some function in R, and that function in R is identical for the px, the py, and the pz, which is really cool. And so now if I switch here over to my Mathematica file, so you can see what I've got here. Here is my R equation, right? I'm setting up my R as a function of x, y, and z. I called this thing n just to have a unique name, but that's that 1 over 4 root 2 pi. I'm calling z equal to 4. And then now my psi 2s, and I used a slightly different psi just to make it unique. I'm defining this as a function of x, y, and z, right? It's this normalization constant. Let's back up to the psi 2s wave function, right? Times z to the 3/2. In this exercise, we're going to ignore the Bohr radius. We're going to call the Bohr radius equal to 1. That's fine for the purpose of this exercise. And then now look, check it out. I've got 2 minus zr divided by a, and we're calling a 1. And so here I've got 2 minus z times r, but remember, r is a function of x, y, and z. And then now that's times the exponential of negative z times r divided by 2. So that takes care of my 2s. And here you can see my 2pz, that example that I worked through, right? It's the normalization constant, or the like half of the normalization constant, if you will, 1 over 4 times root 2 pi. And then there's times the z to the 5/2 power, right? Because I've got that right there. Again, a, we're just calling it 1 for this exercise. And then now look, times z times exponential of negative z times r divided by 2. And then look, I can use this exact same function for the px and the py, right? It's identical except for the px, I put an x. And for the py, I put in a y, okay? And so now I have got all of my atomic wave functions, my hydrogen-like atomic wave functions coded up.